Thank you for having me again. I was here in 2019, but under the different name of Corning. My name was the same though. Yeah, we changed to Amphenol. Cablecon is a company based in Denmark. Amphenol owns two companies in Denmark, Cablecon being one of them, manufacturing shiny parts, being brass connectors, and the other company being Procon, making antenna systems. It's been quite a journey over the last 2 years since we left Corning, because Corning being an American company, quite matrix based, they were governing everything we did. Amphenol is quite opposite, we're on our own. So now we try and make our journey a bit more interesting for our end users, because we can now control what we want to develop and Corning doesn't have to. My history is not from this particular industry. I come from two other industries, aircraft industry and non-destructive testing. And that's why I always tend to dig into details. I am the product engineering manager at Cablecon, and I try to control what ideas we bring to life. Today I'm going to talk about plating. And plating is a very, unsexy thing, I would say. 4 to 5 years ago I had absolutely no idea about plating, and that's why I asked ChatGPT to give me a wonderful headline here. So beyond shine, the art of brass plating and product enhancements is not mine, that's ChatGPT. So let's go on with this. And it's too technical, so it doesn't work because it's not connected to my computer. So what are we going to talk about? Well, the plating, it does provide a climatic shield for the raw material in general. That's really what we want to do when we try to cover up our products. But what are the benefits and what are the drawbacks of the different plating types? We're going to talk a bit about hardness, thickness, filleting, distribution and other parameters of the plating. How does the plating line work? The raw material, the composition of the raw material, and the state after machining. And it may not make sense to you right now, but I hope it all does when we're done. And why does the plating fail? And what should you consider before choosing a plating? Now, you could take this back with you in general, because it doesn't really have to comply to only brass connectors. It could be any product that's plated, any product where you want to pass an electrical current or have other enhancements done to. So you could use it in general. Next one is a picture of just some of our old connectors. They phased out now, but they are shiny and bright once we pull them out of our plating line. And why do we do this? Well, the surface plating is the process that adds a surface layer to the metal, of metal to another type of metal. At least that's the part I'm going to talk about. I know we also have other parts like plastic plating and so on. I only have 45 minutes, so we're going to keep it at metal to metal. And it's really done to prevent corrosion, enhance solderability, improve the hardness of the substrate, reduce friction between moving parts, enhance reflectivity or even reduce it, shield against radiation, improve the electrical path, stabilize pin performance, and improve the overall aesthetics appearance of the metal component. There's only 4 slides with text on. Okay, so this is a very old style RF connector. This is airborne transfer with variable low frequency PIM. Really just joking, but notice that you have 2 different platings on the same product. So you can have different looks even though you have the same function. What is the surface plating then? Well, the plating can be described as a surface covering where a metal is deposited on a conductive surface. And without the metal plating, corrosive raw metals would only last a fraction of their potential coated lifespan. So by putting on a hard and corrosion-resistant surface, we simply spare the raw substrate we have underneath our raw material. There are also coatings. So what's the difference between a coating and a plating? Well, it's really that plating is done electrically. So coating can be done really by simple techniques like using a brush. And next one, that's the last one with text on. Corrosion and oxidization and the resistance towards this. When the component is deployed into a chemical hostile environment, and it could just be salt water, the protection on the surface from the corrosion, in this case I mentioned galvanic corrosion or chemical damage, is another frequent reason for having a surface treatment of the component. And I think we all know, in the good old times, we had this hot dip sink coating that we all know from any truss construction out there and in high power fields or whatever. And this is a sacrificial barrier, meaning that it will, over time, erode. It will simply galvanically erode, thus protecting the base material. So it's the sacrificial part. And how can we obtain a comparable level of corrosion protection in a different way? Because we can't do hot dip sink protection on our brass connectors. It simply doesn't make sense because we cannot control the amount of material we add. So we have to use other techniques. Some of these techniques are electroplating, electroless plating, and immersion plating. I'm not going to go into depth on all of them. I'm going to talk mainly about electroplating because that's where I have my knowledge. We have our own plating line. I'm going to show you some things that we found out over the years, some that I just realized, and we'll see where we end. Before you get to a coating or plating, you really have to consider the galvanic table of your metals. You don't want to have more than 500 millivolts between the two materials you're using or combining. So that would be this light amber part and the green part. That's really the 500 millivolt section. Now you can of course go lower and sometimes you can go higher, but don't try and do it. It will usually cause galvanic corrosion. I was lying, there was one more with text on it. So the electroplating. What do we do with electroplating? Well, it's a process where we simply take, let's just read it. The most commonly used plating technique is electroplating, and in the process of electroplating, positively charged metal ions are dissolved in a chemical solution, and the material that is going to be plated, which is on the negatively charged side of the circuit, is drawn to the positively charged metal ions. What's the effect of this? Well, it's a protective coating and a very decorative finish. It could also be a modification of the quality of the product. We can also add material in different regions of our product. So we can control where we add the material. Electroless plating is more, well, it's without electrodes really, so you don't have an anode and a cathode. It involves a chemical reaction that facilitates metal atom reduction, and in other words, when metal ions or particles in a reducing agent solution come into touch with the catalytic metal, they are transformed into a metal solid. As a result, a thick layer of plating metal is applied to the metal. This is something that usually goes under the name flash plating. Some of you might have heard the word flash gold plating. The layers are usually also quite thin. What are the effects of this type of plating? Well, since we don't use electricity and we don't have the same amount of chemicals involved, it's much cheaper and it is a bit faster. So it is less expensive. However, it's slower and it's unable to produce thick platings, as I mentioned. A drawback is the high amount of porosity, meaning that the end plating, the plating on the product, does not have the same density as electroplating. So it's porous, meaning it can absorb or you can have chemicals passing through it. It's also quite often used for colored platings. So if you would want to have a black nickel, which looks very sexy, some think, you would simply add dye to the nickel and use electroless plating. However, this also adds to the porosity, lowering the density of the nickel plating itself, so that would make the product not as protective. And lastly, and not least, the immersion plating. which is a solution of ions from a more noble to a less noble product. So going from gold or silver or platinum and so on. We know this technique mainly from, well, I do, from hi-fi connectors, which is, it should improve sound. They use immersion plating, so you can buy these terribly expensive palladium connectors for your hi-fi, and really there's nothing on, it's just the looks. Now a picture, wonderful. This is a very old test made some years ago. It's not by us, I just took the data and replotted it. It's looking at the difference between nickel, silver and miralloy. Miralloy being white bronze plating. PIM, which we are testing, is the passive intermodulation of the parts. And as we can tell here, quite quickly, it's self-explanatory that nickel really does not provide a very good PIM. However, both silver and white bronze does provide very good protection or PIM performance. So what kind of platings do we know of, or can you guys think of? I guess the very old one is just copper on PCB. That's the same technique. The newer ones at least. We've got nickel and nickel iron. We've got microfabrication. We've got engineering and functional coatings. We've got decorative and protective coatings. I would say the last two more or less cover the same field. We've got sacrificial coatings, like the hot dip or cadmium, and we've got alloying coatings. Now the one that Cablecon is using is the nickel tin, down here in the alloying, and this is actually white bronze. So copper, tin, zinc is white bronze. As you can tell, it's made from 3 different alloys, so you can actually have different variants of white bronze. You can have yellow white bronze and red white bronze and so on. What industries use plating? Well, mainly automotive and then electronics. The rest is just distributed all over. But if you look for a good partner within the plating industry, go for automotive. They really know a lot about plating. There's a lot of things to think about on a plating, and this is not mine. I have used several different sources. Not everything is ChatGPT. This is same test from Miralloy, but it shows what some of the benefits are and drawbacks are for some of the plating. As you can see here down in the bottom, if I can find my cursor, you can't see it, I can. Oh, there it is. See, white bronze and yellow bronze, so it's different alloying of the two same platings. There's a word here, leveling, and it says here that it's a bad thing if it doesn't do leveling. Well, that all depends what you want to get out of your product. And talking about leveling, I'll just touch base with that quickly. Here we have a comparison cross-section of components with electrolytic nickel plating top pictures and electroless nickel plating in the bottom. However, I guess you can see the filling, how it fills the corners and so on, the nickel, whereas the electroless nickel plating doesn't do that. Another thing is that on cavities, saying if you want to be sure that you coat your inner parts, you can always do that better with a non-filling plating. If we were to take nickel compared to nickel tin, it would be the same matter. So nickel tin will behave like the electroless nickel in the bottom, even though it's electrically plated that way. So you can actually have drawbacks and setbacks depending sorry, of the filling function. That's a white page, but there's something on it, and this is really just talking about the hardness of the product. You also have to consider what's the hardness of the raw substrate that I'm working on, and I actually put it in here. It's brass, so it's around 170 Vickers. And when I add different platings on it, I have to bear in mind that if I use extreme forces on my parts, I might break off my plating simply because it's too hard, it's too brittle. It does no longer adhere to the base product. It chips off. And it all depends on how well it adheres. This is some of the analysis parts we can do with the PIM, actually, is to see how well it adheres to the base product. So how does the plating line work? Well, regardless of the plating material, as long as we're talking electroplating, we could actually consider the anode. I'll just point it here. This is the anode on the plating line. This is the cathode, being the part that we want to plate, and an anode and an anode again. Sorry, all these ends. You could actually consider it being a spray gun, spray painting. And the paint is solidified through the electron beam in the dilution that we have. A setup for plating line is rather big. This one shows drum. So drum plating, so we have a few drums here. We have both drums and racks. This is a dual line setup, so you have two drums, etc. But in general, we have pre-treatment, cleaning, we have plating, and we have post-treatment. This part is about silver, so you also have passivation on this part where you make sure that it's no longer active. But again, it's just rinsing cascades. It's a very big setup, and there's a lot of things to control. And a few slides later, you'll see how much we have to control to make sure that we get a consistent product out of this plating line, or such a plating line. Racks, I just mentioned racks. As you can tell, we have connectors here hanging on racks. These are hanging on a copper bar that's providing the power in the solution in the bath. As you can tell, maybe you cannot. The connectors are spaced differently because remember the spray paint, we have to coat them on each side. So if they cover each other, because of the camera angle, you would see that these cover each other now, and that means that you wouldn't get any plating on the back side of those connectors. So we have to make sure that we use racks that are aligned with the parts that we want to plate. And we also have to make sure that the surface area is correct, so we don't have overlying corners, making shadowing parts and so on. How do we measure this? Well, we measure the thickness with X-ray fluorescence. Don't know if you guys know X-ray fluorescence. It's mainly used for positive material identification, but also thickness measurement of different metals based or plated on other metals. And what we do simply is add energy through X-rays to the top surface and do an analysis of the fluorescence, the light spectrum that it sends back. That way we can measure the thickness of our plating. A picture of the anodes I just mentioned. So these are spray gun parts here, hanging in a plating tank. And the picture next to it is a rack. So there are no connectors on it, but you can see all the strings here where you would have the connectors hanging on. Distribution on such a rack is not easy, because now you guys are thinking, okay, I dip my parts and I pull them out and I get parts with X amount of microns on it. Unfortunately not. So we did a test to verify how critical is it for us to make sure that each contact point in the distribution chain is the same or has more or less the same resistance. So we added clamps on top of both the anodes and the racks themselves. So before we did that, we had this distribution of thickness. So we did 10 measurements in each spot on each connector. One being the back side and one being the front side. Blue is the front, yellow is the back side. The larger the circle, the less consistency in plating thickness we had, meaning the bigger spread. So the smaller the circle, the less spread we have. Each bar here represents the limit where we have to be within. So that's our lower limit and our top limit. So you can see these two actually should be here, and so on and so forth. So it's not a very good measurement or technique we used here. And then we just added the clamps just to see what happened. And this is the picture we get afterwards. As you can see, it really changes the distribution quite a lot. So it's really critical to know what to maintain in the electrical circuit path, because you've got a lot of contact points that could fail and give too high resistance, meaning less plating or less consistency in plating. Sorry about that. I have so many notes here, I can't see them all. Yeah, another thing I have here, we can also control the distribution by using guides. So on the anodes, we can put plastic guides on to sort of narrow in the field, the particle field or the particle flow we get. Not the electron flow that we get from the anodes, we can't control that with plastics, but at least the particle flow we can control, thus making sure that we get a better coverage. This is a plating line, this is our plating line. In the end of the plating line you can see some large plates here, and these are plates used for selective cleaning. We do that every weekend, and simply because using such a plating line builds up tremendous amounts of debris in the plating material. And we don't want to have debris in there. I'll show you later why. But we use a cleansing cycle every weekend to clean out this debris. Right hand side is a rack transition, just showing you, it's a small video and we don't have awesome audio on it, unfortunately. We're not finished. Absolutely, there's no audio. But it's just the robot just moving the racks from one container to the other. What I want to pay attention to here is the cross-contamination from tank to tank, because you see all the dripping. Now we start to move the racks, and it drips quite a lot into the next tank. So that means that all these tanks have to be replenished all the time. It's done automatically by an automated system that we built. So, left-hand side. What happens when we start plating all our components? Well, we also start to plate everything else that's in there that has a conductive surface. So that means our racks are usually, or they are, covered in PP plastics. So we only have the small outer part of each hanger to put the parts on. However, as you can see, we get massive buildup of nitin, nickel tin that we use, on the racks, and that has to be cleaned as well, because adding that or having that buildup, it's not just, it doesn't look sexy of course, but that's really not why we remove it. It's because we're adding to the total surface area that we're trying to plate. And when we plate, we have to control the ampage per square inch, or whatever area we're controlling. So adding that amount, uncontrolled amount of surface area makes, well, we can't really control the thickness that we want to have. And right-hand side is these plates, selective cleansing plates that we use. And as you can see, there's quite a build-up on them. Here's a picture of a bit more build-up on a nitin hanger. And if we go very close to these selective cleansing plates, you can see that that's a really big build-up. They run 48 hours every weekend at 50 amps, and we usually collect around 2 millimeters of debris on these plates. We're using plates and not just racks with random connectors on, because the plates are, see if I can go back, you can see they are bent in a specific shape, and that's to control the ampage in the corner areas to make sure that all the heavy particles are taken out of the nitin. Okay, going back some years, we did cleaning of these racks manually. And you would say, okay, so what? But really, it's nickel and tin, and it really does adhere quite a lot. So you use quite a lot of force on air pliers, and doing so would really just make nickel powder that could be inhaled. So that's not really wonderful to inhale. So we had to do it in a completely controlled environment, and it would take forever really, and nobody wanted to do that. So we built Daisy. We named her after our queen. She's very reserved, she likes to stay for herself and sits in a glass box. And what she does is just clean racks. And that's it. As up in the top of the left-hand picture, you can see there's a small color coding, and that relates to the racks. So each rack type has its own color coding, meaning that when we put them in there, We can tell them what color coding it has, and Daisy knows what rack it is, and we'll clean it, turn it around, and clean the other side as well, meaning that we now have our hands free to start cleaning our tanks instead, because they also get full of debris. This is from half a year's use of a plating line. This is just one of the tanks. We run a dual setup. As you can see, we have anodes, old anodes. They really wear out fast, about half a year. They're about this thick when we start, about 1 inch, 25 millimeters. And that over there is really just debris from the bottom of the tank. And why do we have to clean that out? Well, here I'm showing you a picture. This is just tin on copper, but it's showing you how much debris you can actually have in a plating. So this is debris from the plating line itself, meaning that the paint that we have is not clean anymore. This is another picture. This is a very thick substrate, and this was actually a test made with cyan copper on nickel. And it's, again, to see how much debris we can actually collect by increasing the ampage when doing selective cleansing. However, it does really give you a very good picture of the amount of debris that we see. And this, of course, also limits the amount of use of a plating line, because our plating line, we use brass connectors. We plate our brass connectors with nitin. Nitin originally was made for the medical industry and actually for hips. But they quickly realized that that wasn't very good due to ammonia and brass. Regardless, what if we were to plate medical instruments with our nitin? We could do that. We have nitin. Or can we? No, really we can't. Because the debris in the plating line is also from our substrate. And we have lead in our substrate, meaning that we will contaminate the nitin with lead. And we don't want that in medical equipment. So there's a very, you also limit your own use of the plating line with the substrates you put in, with the raw material you actually put in there, because of the cleaning that you do. This is another test or trial we made, trying to govern or trying to control the thickness of our products. And this is done by controlling the ampage and the distribution. How well does the electron flow from the anode towards the product? Is the anode, the spray gun, is that too big? Is it too small? If we look at an anode that's, in our case, it's square, we get the main distribution from the corners, the corner effect, the diffusion, and not from the main part of the anode. So it's really something that we have to take into account when placing our racks and also placing our anodes, because they're not placed consistently with 30 centimeters apart. It's in a different pattern, and sometimes we have to change the position of the anodes because of the parts we're plating. So this test shows you that we just gave it a shot, and as you can see, we're not very consistent within our limits. We have 5 to 12 microns as a limit, and you can see we're actually completely out of that scale. So we tried to adjust the ampage, and we ended up with this, oh sorry, that was a bit too fast, ended up with the lower one, so you can see we can actually control some of it, and also making the lower chart, hang on a second, the last one here is where we adjusted the anodes themselves. So keeping the same ampage, but adjusting the size of the anodes. And as you can see now, we get a really good coverage, a thickness plating that's acceptable. Going down to this substrate part that I keep talking about. That's one of our general geometries that we use. Standard copper, zinc, 39, lead 3, a standard alloy, and if I can get my mouse over here, there you go. So that red box here is being enlarged into 500 micron picture, then to 100 micron, and then to 50 micron. And I'm going to focus on the later here, because we also did some acid edging on this one. So you can actually see the alloy here. It's quite fun, or at least to me. This is the copper, this is the zinc, and that's the lead. So the small black parts are the lead. Now if we go down to this part, and remember this is from the inner part of a connector, The inner part of the connector is usually made by a drill bit that's pre-shaped. So meaning we have as little as possible deformation because we're not running a contact point deformation, we're using a drill bit. So the deformation zone is rather low or small. You can see it's around 36 microns here in the brass part. However, do notice that the angular shape or the geometric shape that we have up here has been disturbed quite a lot, and we see that we have a tendency to follow towards the right side, meaning that we have the pressure this way on the drill bit when we made it. That also means that we open up our structure. We start to pull out, the drill bit simply pulls out the zinc, the lead, and leaves the structure open. This is of course on a microscopic level, however, that's what's true. So when we start dipping our brass connectors in our cleaning solution before we plate them, all this excess material falls out of the connector into our bath, and that's really what is the debris that we get, the amount of debris. And lead is unfortunately not a very good component in a plating. Now this one is a lead inclusion on the surface of a brass piece. You wouldn't be able to tell, it's very small, but you won't be able to have the plating adhere to the raw material, it won't adhere to the lead, and you will simply have spalling of your plating. The other one here shows you the deformation zone again. This is with the nickel plating on, but actually you can tell that you have small spots between the plating and the raw substrate. So that means that it does not adhere fully. And I'm going to go a bit deeper into material, I'm sorry, but it is essential for understanding. What happens when we make the material? When we make the alloy, when we make the brass or the copper, doesn't really matter what kind of metals that we use, they're usually made up in slabs from the beginning, meaning a big pot of melted metal that's poured into some sort of shape and we let it harden. What happens when this part hardens? Well, the metal that we melted originally may not be 100% pure. Well, actually, it's not. We know that we have contaminants in there, and these will solidify once these will follow the solidification of the metal on the front, let's say, on the wave. So where it solidifies, it will move all the particles in front of it. Meaning that once we have a slab, this is part of a slab, and once this has hardened and solidified completely, all these impurities will be located in these points, the diagonal points in each end and also on the plane in the middle. And why am I telling you this? Well, because when we start extrusion process of a slab, making and forming it into a bar, into a hex bar, whatever we want to machine afterwards, it's really critical to know the amount of impurities in the slab when you are manufacturing these bars, because they might end up in the surface, and you don't want that to happen because then you'll end up with bad plating. Unless of course you have a product where you remove half the brass before you plate it. Again, you have to be certain about this. That's also why it's not a good idea to use cheap brass from other regions of the world. You often see that they have a tendency to put in other things like cardboard or cats or something, and that will generate a lot of debris in the brass. The manufacturers of the brass bars are of course using different techniques to try and assure that they don't have any surface defects. They're mainly using eddy currents, and eddy currents are great. They're super fast, but they only check the surface. So they only go down to about 1.5 millimeters of depth. Meaning that even though you have a certificate of a brass bar saying that it's without any defects, it's not. It's only the outer 1.5 millimeter you check. If you have to do 100% volumetric inspections, it would have to be UT, and the brass would be 10 times as expensive. So we don't want to do with that. We'd rather throw out a few connectors here and there. So this is a parameter that we know of and that we of course have to maintain control of as well. So what happens in the plating when we start to magnify it? On the left-hand side, you can see there are some micro cracks in that plating, and on the small spheres that you see are actually lead in the plating. You see, it doesn't compute. On the right-hand side, you can see that's a suction hole in a brass bar, and we did not get any adhesion on the plating whatsoever afterwards because this small suction hole was full of cleaning agent. So again, surface condition is also something that we really have to pay attention to when talking about plating. Now, I did show you a similar picture earlier on. This is a brass. There's no edging on it, but you can still see the way it's been machined, and you can see how open it is in the substrate. You can also see the nickel plating. That's 6.34 micron, just as supposed to, I guess, from this manufacturer. It's not from our facility, this one. There's a Danish company called Struer who does a lot of chemical research, and I borrowed a lot of pictures from them. But unfortunately, what is in this one, I'll use my cursor, sorry, forget it all the time, are these. They're actually cracks. They're called mud cracks, simply because of mud in the plating tanks. Lead, zinc, old cathodes and a bicycle, whatever is left in there, it will all be mixed into the spray paint, thus reducing the strength of the spray paint, and quite often it ends up with plating that cracks. And you won't be able to tell. You can't see from the surface. The problem is that it's completely open to the environment. It's as if you don't have any plating on it. It will suffer from stress corrosion the second it sees any ammonia or salt, because it runs straight through the cracks and into the open part. Remember the deformation zone of around 30 microns in the brass? It will run directly into that part and it will start stress corrosion. And when I say that, it will, because this is brass left in just open air. So that's the surface after milling. It's self-explanatory, I think. 200 hours, 600 hours, and 1200 hours. Now, if you think of the former picture where we had mud cracks in it and open substrate, that's what's gonna happen underneath the plating. Eventually, this part will fail. I'm coming to the end. Oh, more text.
Is that a threat or a promise?
This is actually the last but one slide. Okay. So what should we consider before we choose our plating? I hope I gave you an idea that it's not as easy as one would think. You can't just say, okay, I want some red nickel on this one. You really have to pay attention to the product and where you want to use it. So we should consider, of course, as I mentioned in the very beginning, the galvanic table and the position of all our metals in the product chain. So both the raw material, the plating, and whatever we connect to. It could be both the cable, it could also be in the interface end. And are we talking full or partial coverage? Are we talking inside and outside? Does the end user have, oh sorry, skip, no, that's right. Does the end user have certain restrictions or needs, color or electrical? I mean, it could be, we have quite a lot of military connectors that we're building right now, and they can have absolutely no reflections on their shiny parts. Doesn't compute, but I guess you can tell that they use a lot of dye in their connector platings. Do we need a full corrosion protection or just a shiny thingamajig? Do we need limitations on the geometry, meaning should we worry about the filling? Could that filling maybe destroy some of the mechanical features or make sure that they don't happen or work the way they're supposed to? Do we have electrical performance to consider, like nickel versus white bronze, PIM performance, return loss performance, and so on? And would it be beneficial to use different platings for subcomponents, therefore thus reducing the friction between components? Or are we limited in other ways of, let's say, the hardening or the hardness of the plating itself? We have a product, a very old product. It's called a hex crimp. I guess you all know it from the very good old days. That cannot be covered with nitin. Nitin is simply too hard. So if you crimp a hex with nitin on it, you will just have, shiny fingers and not a shiny connector anymore. So that has to be plated with a more soft material. We use white bronze. I'll show you quite shortly why. Is the plating solution a sustainable source? Reuse of water, etc. There's a lot of use of water in the plating facility. we made sure that ours is made such a way that we always replenish with the less dirty water to the more dirty tanks. So we only add water in the beginning of the chain and we're moving water down the chain to more contaminated water. And is the plating line ROS compliant? That's a really big issue right now. Lead inclusions, the use of lead and how we clean the water is also a very critical part. I mentioned just before, should I choose white bronze over silver? And this is, I'm going to show you two pictures. The first one is return loss. It's the same connectors made with silver and white bronze, just to show you the difference. So here I'm comparing the return loss values from the connector. And as you can see, there's really no consistency in one being better than the other. We have some slight changes. These are most likely due to mechanical differences, changing the impedance plane, and that's it. But if we go to pin testing...
Excuse me, is that both sides of the connector are white ones? So you've got a male and a female white ones connector?
No, only a single connector. We gate them out. We use the time spectrum to gate them out. But regardless, it would...
Surely whatever you're mating against is...
It would be, yeah, okay, if that's the question, yes, we're mating against the same.
Right.
Yeah, correct. Sorry, I misunderstood you. So if we go to the PIM, you can see that it's a different picture, and the white bronze is actually quite better in PIM performance. Why is that, really? Well, think of it. Remember that I showed you the alloy of white bronze? It's almost made of the same material as the alloy itself. So it bonds directly into, because they're native to each other. We don't have a fourth party that we try to put on. So that's why we almost always get better PIM performance with white bronze. So, last picture. It's not a picture, but if you get all these things settled and do your due diligence, you might be able to pull out your shiny parts from the slurry of the plating tanks. And that concludes it from me. Thank you. I'll leave the picture.
Questions?
Yep.
Well, wow, that was very enlightening. How does your QA work with everything I've just heard and so many items like that screen?
Everything is catalogued. Every connector has a rack, a color coding for a rack. So we know exactly the surface area that we put on the rack so we can control it. QA has been through this entire system, and every single rack has reference measurements on it. So we know the exact value from each rack.
Oh, but I was thinking about the final output.
Yeah?
When you've got hundreds, thousands of these.
Yes, you're right. I also have to be honest here and say, when we look at 75 ohm products, and we are right now, we don't make those in Denmark. In Denmark, what we do, but those are only the bigger ones. So the very small drop connectors are not made in Denmark. We make everything from Series 2 and up in Denmark on 75 and 50 ohms, and that means that it's mostly bigger connectors around this size and up that we make. So it's not that high amount of connectors, but yes, we do a lot of measurements, a lot. Every week we take samples from every tank and send off to make sure that we control all the chemistry, that the pumps have the right flow, that they replenish the right amount of sinks and so on to the baths, that we don't wear our anodes differently. They have to have the same shape all the time, otherwise we get uneven distribution. We have to make sure that all the contact points on the anodes as well are maintained and so on. So there's really a lot of work. It's not easy to maintain a plating line. It's quite simple to make shiny parts, but not functional shiny parts.
Thank you.
What kind of plating are you guys doing for any kind of glass or optical connections?
We don't. You know, we are the dinosaur. We only work with brass. But in Amphenol they do, but in Cablecom we don't. So I don't know. I won't be able to tell you. Unfortunately.
Any more? Thanks, Bill.
Yeah, we've got a few cabinets that have got F connectors in and they're outdoor and a bit damp. Whenever you go there, there's usually one or two that are to a degree. Is this an indication of poor quality manufacture, or is it something that can be avoided, or can you buy connectors that don't corrode like that?
Yes, well, all our connectors undergo 1,000-hour salt spray testing, so we of course are compliant with that. It doesn't mean that if you jam it up with something that will start a galvanic reaction, that they will last 1,000 hours in salt spray testing. And we do salt 1,000 hours. Some others do 158, which is the normal standard for heavy maritime use. So if you get your hands on connectors that are not tested to 1,000 hours, but maybe only to 158, then you might have an issue. But it could also be bad quality, yes. And it could be, maybe not of the substrate itself, it could just be a bad plating. Yeah.
When you do your 1,000 hours, do you current pass at the same time?
Do I, sorry, what?
Do you pass current through the connectors?
No, we don't. We don't.
You mentioned sort of the physical layer damage that can occur just through the manufacturing process. Do you ever anneal high-value parts? Like, could you anneal it over time to sort of repair the surface, or is it just cost?
We do annealing, but we only anneal on parts that we have to mechanically deform. However, we do normalizing on thin parts where we know we could have issues from machining. So we will normalize them by simply just baking them 2 hours for 250 degrees, removing all the stress. Correct.
Are there any more?
But
Good.
we don't want to. It's adding to the process. And I have a small story I can add to this, because we actually did an investigation of whether it's needed or not to control the feed in the CNCs. Simply how much damage do we add to the parts. So we did a test. We had this connector. It was actually working in a really harsh environment. Pig farming. A lot of ammonia. And usually this connector would be machined with feed 2000 on the parts. It doesn't ring a bell with me whatsoever, but it's a high number, very fast. The problem was that the product wouldn't last more than about 150 hours in the environment that we tested it in, the ammonia environment. They would fail, simply just snap open, stress, fatigue. So we machined them with a feed of 100 instead. And all of a sudden they lasted 950 hours. That was the only change. Then we removed the machining and bought hex bars, and now they don't break. So, I mean, there's quite a lot of ways that you can control your product, if you know the failing ways. Yes?
Any more questions about sexy plating? No? Thanks very much, Søren.
You're welcome.